Stephen. So it's my pleasure to introduce Professor Stephen Smartt from Queen's University, Belfast in UK. Stephen has been a force in time domain astronomy for almost 2 decades now. He leads the various projects, including ENGRAVE, PESTO, ePESTO, the time domain aspect of ATLAS and Pan-STARRS 1. And if you look him up on ADS, that will say it all, with 306 papers and a whopping H-index of 81. Stephen's most cited paper is one that I know I've used in classes here. It is his 2009 annual reviews paper on identifying progenitors to co-collapse supernovae. So I hope many of you have read that paper. It's fantastic. Stephen's fantastic work in time domain has led to many prizes, but I'm very excited to hear his talks. I'm not going to go through them all, except highlight the 2 most recent ones, which are amazing. One is that Stephen was elected a Fellow of the Royal Society just last year. And just a few days ago, it was announced that Stephen was awarded the Herschel Medal by the Royal Astronomical Society. A medal that many fantastic astrophysicists have received, including our own Professor Neugebauer. So with that, I don't want to take up more time, and I hand off to Stephen for his talk. Thank you.
Thank you, Nancy, and thanks for the invitation to talk to you. I'm sorry I can't be in Caltech, but I hope I can do that later this year, if not next year, and meet many of you. So I'm going to talk about mergers, magnetars, and multi-messengers. I won't dwell on the multi-messenger aspect too much, although I show a picture of LIGO here, mainly because the rates of detections of binary neutron stars were a little bit lower in 03 than we had expected. But that the detection of a neutron star merger and the kilonova has driven a lot of it. The strategy of the work that I'll talk about. And let me just see if I can change my slide, which is not quite working. Okay, now it's there. So the outline is I'll give an overview of what we've been doing from the perspective of wide field surveys and the diversity that we've discovered in stellar explosions and mergers, as you have done with ZTF, of course, and other groups around the world have done with recent wide field surveys. We've all discovered, I think, quite an unexpected diversity in the transient population that we've discovered in these surveys. Raising questions such as what is the power source of these? For many of them, it cannot be nickel 56, which drives most of the supernova-like transients that we've known about for decades. Related to that, how much mass is ejected in these mergers or explosions? And critically, what's the chemical composition? Because that's a key factor in determining what the nature of the sources are. I'll mostly focus on our searching for fast transients. These have been different terms have been used. Rapidly evolving transients is the one the ZTF group have used recently. It encompasses all of these fast evolving, fast declining, and fast rising objects. And we'll see that kilonova fall into this group. I'll talk also about a lot of our work here is focused on taking spectra of these objects, working out from spectral modeling, then working out what the composition is. And I'll hopefully get, if time allows, I think it will, to talk about what we've been doing in determining if we can see any signs of gold and platinum in the spectra of the kilonova from GW170817. So I'll highlight just 3 graduate students who have done a lot of the work that I'll talk about. Owen McBrien, who's just finishing, James Gillanders, who's been doing the spectral modeling that I'll talk about, and Michael McCann, he's not my student, but he's calculated some new atomic data for the gold and platinum work that I'll highlight. It's just a little bit of a delay there and me changing, that's okay. So let me just ask you a question, and as a remote talk, it's hard to get audience participation. But let me ask you a question. What do you know what links these two images with supernovae and California? So there is a California link as well. What is the link between these two images, the field of supernovae and transients, and California? I'll just give you a few seconds to think about it. I won't ask for answers online. So I suspect some of you may have got the link between Andromeda and supernovae, but not quite the link to Ireland. So of course the link is the nova in the Andromeda galaxy, discovered in 1885, and credited to Ernst Hartwig, who discovered it from Tartu in Estonia. 20th of August in 1885, he discovered this, but of course at the time, no one realized the significance of this nova, because the distance to Andromeda in 1885 wasn't known. And it was only when Hubble estimated the distances to local group galaxies that in the 1920s, and even in the 1920s, then there wasn't any realization of the significance of this until Zwicky came along 1934 with BAD and said, well, if Hubble's distance is correct, then that nova in Andromeda in 1885 is 2 times 10 to the 9 solar luminosities, or 10 to the 4 times brighter than the most luminous stars in our galaxy, or the most luminous novae. And just from that measurement, just from the estimate of the visual magnitude from 1885 and Hubble's distance, he suggested, BAD and Zwicky then suggested, the physical nature of this object is likely to be the core collapse in a massive star, that the gravitational energy release is what has driven the luminosity, that a neutron star, an object like a neutron star, was formed. Now, this was 1934, only 2 years after the discovery of the neutron, and the first pulsar was discovered in 1968. And he also suggested these could be the source of high energy cosmic rays. So just from that one measurement, 2 measurements, the magnitude and the distance, quite a physical foresight to come up with this theory of the luminosity, which was pretty amazing at the time. So what connects it to Ireland? Well, actually, the discoverer of this was actually Isaac Ward from Belfast, with his 12-inch refractor here from the centre of Belfast, who discovered it, was the first to report its existence on the 19th of August in 1885. It's just he didn't send out the telegram quick enough and tell everyone. So Ernest Hartwig certainly did tell the world before that, but it's almost certain that Isaac Ward, who was a well-known astronomer here, Victorian astronomer, did catalogue the object on the 19th of August and just missed his opportunity for world fame. Unfortunately, the next supernova that I know of to have been discovered from the island of Ireland, and that means a photon has hit an instrument on the island of Ireland, and that person has discovered it, was not until Dave Grennan, who lives in Dublin, in 2010, discovered the next supernova from this island. So I think that is why California is much better known for supernovae physics and transient physics than Belfast is. Okay, let me just give you an overview of what drives the luminosity in type 1 supernovae and type 1a supernovae in particular. The most common supernova we find in magnitude limited surveys of type 1a supernovae. Some of them may come from double white dwarf mergers, others from white dwarfs in a binary system, sequence companion. Probably both of these channels play a role in producing the 1a population. The key thing here that I just want to highlight is what produces the luminosity in the timescale. And so if a Chandrasekhar mass white dwarf exposes carbon and oxygen, burns to the intermediate mass elements, magnesium, silicon, sulfur, calcium, and critically nickel 56. So you can't produce stable iron from a carbon-oxygen thermonuclear runaway because the neutron to proton ratio has to be preserved. So that means nickel 56 is produced, which is radioactive, and that decays to cobalt 56 and then iron 56 with half-lives of 6 days and 77 days. So that produces the stable iron that we see in the universe. but that sets the time scale for combination between those decay time scales and the ejecta mass of about somewhere between 1 and 1.4 solar masses from a white dwarf, then sets the time scale for the light curve and the time to get the peak magnitude. So that drives that nickel 56 is the key here. It's the key radioactive element that drives the luminosity in the bulk of the normal supernova population that we see, type 1a supernovae, type 1b Cs, and some of the luminosity in type 2s. But that general paradigm of nickel 56 driving the luminosity of the transient sky has been completely changed in the last few years with wide field time domain surveys and follow-up of objects found. You can see this now quite famous picture, image of a famous plot from Sri Mansi and Peter Nugent from the days of dating back to the PTF of time scale versus peak luminosity of transients. And the gray area is the traditional area of where most of the transients in the local universe are found. Thermonuclear supernovae, the type 1As, again driven by the luminosity, the energy produced by nickel 56, and the core collapse region, some of which mostly driven by nickel 56. But then the wide field surveys have filled in large regions of this parameter space, very luminous objects, the very superluminous supernovae, up around 10 to the 44 hours per second at peak, and faint objects in between supernovae and novae, which have been called various things. The objects in the top left are relativistic explosions, which the luminosity there is not produced by thermal radiation due to, say, radioactive heating. But the fact we filled in the areas of this diagram plot, I'll show you, means that not all of these can be driven by nickel 56, and there must be other powering mechanisms for these objects. The first order, the y-axis here is driven by the heating rate, whether that might be due to nickel 56 or some other radioactive element, and that's combined with the x-axis is driven, typically the time scale is driven mostly by, well, the heating rate is important, but the first order is driven by the ejecta mass. So the larger the ejecta mass, then the longer it takes for energy which is produced from some sort of powering mechanism in the transient to leak out. So typically larger mass transients which eject larger mass typically have a longer time scale. Of course, these two are coupled. And the coupling between the time scale for energy release and the ejecta mass and its opacity produces the diversity in this diagram. And I just highlight some surveys here which have influenced this field recently. Which are produced from emerging neutron stars, live in about this area of the parameter space. So they're fainter than supernovae, of course. They're much faster, and they're lower ejecta mass, and that means that the timescales are faster, and the predictions and the one event that we have show that the velocities are very high. So this area of the parameter space is where we might expect emerging neutron stars to live. Now, ZTF and DES have produced a couple of papers recently showing where these rapidly evolving transients, and they've been called fast evolving luminous transients, or FELTs, or FBOTs, fast blue optical transients, before. And they live in a parameter space which there's a large range in their luminosity, some around the same, similar to supernovae, some a bit fainter, some significantly more luminous. They tend to be quite blue early on. So if you look at the ZTF plot here, this is a magnitude limited bright transient survey, magnitude limited survey, worked recently by Dan Purley and collaborators there at Caltech. This region of parameter space of order rest frame duration, this is the time over which an object has its luminosity is the time taken to go from peak to half its luminosity. That's roughly the duration which is plotted here. Similar for the DES objects. The DES paper was more focused on their host galaxies. So here in the ZTL plot, you can see some of the well-known fast transients with a diversity in their luminosity. If you assume that these are diffusion spheres powered by some mechanism, then the time scale goes as opacity times ejecta mass divided by velocity, and the square root of that term. So for these to be fast, the ejecta mass must be pretty low. And so if you compare them to type 1a supernovae, so they're a factor of a few, maybe a factor of 10, faster evolving than type 1a supernovae. So their ejecta masses have got to be of order half the solar mass or less. And that usually means it's a compact star that has produced those, rather than being a large massive stars, pointing towards low mass compact stars that produce these rapidly evolving objects. And of course, two compact stars that we know of that can produce electromagnetic radiation are mergers of either white dwarfs in binary systems or neutron stars. Neutron star mergers produce electromagnetic, both are predicted to produce electromagnetic emission as well as gravitational waves. And for several decades, they've been predicted to be luminous enough that they should be detectable not just in gravitational waves, but also in our optical surveys. And the last 10 years or so has been taken up by many of us trying to find these types of objects, whether it's white dwarfs in merging systems or neutron stars in merging systems. The first confirmation that this occurs was in 2017, of course, when the gravitational wave event 17 was found in coincidence with the weak GRB, just 1.7 seconds later. But it was actually the gravitational wave sky map that then led the detection of the optical counterpart from 8 teams within the first 11 or 12 hours of the gravitational wave event being discovered. So many teams observed it on the first night in Chile and found the same source, more or less within about an hour of each other. They discovered this source. It was first spotted by the Smartt team in NGC 4993. But this is a well-known discovery and story since 2017. It was discovered, and so what was observed after that was pretty remarkable. That we saw a bright source that you can see in this little movie here, bright blue source, coincident with NGC 4993 that faded rapidly, and it reddened rapidly, faded within a period of about 2 weeks, and the afterglow was detected of the GRB was detected for several hundred days afterwards. This can be modeled simply from a low, if you assume that the ejecta mass is low and the velocity is high, which it needs to be to reach this luminosity within 11 hours of merger. So a velocity is required of around 0.2 c, ejecta velocity, and the peak luminosity and the decline rate means the ejecta mass has to be around somewhere around 0.2 to 0.4 solar masses. And various models, both sophisticated and simple models of the light curve of this transient, indicated it's a very fast moving velocity, ejecta velocity, combined with a low ejecta mass, and that produces the peak luminosity and the decline rate, with a heating rate which is described by a power law, so T to the minus beta. And so the simple models that can reproduce the overall luminosity require this heating rate, which is a power law function, and models of nucleosynthetic trajectories that produce heavy elements that then radioactively decay. Predict that the powering source from a kilonova, if it is produced by heavy radioactive elements, should indeed have a power law, and that minus beta term should be about minus 1.3. And that fits pretty well the observations that were taken by many teams. So there's a very consistent picture of a low ejecta mass, which was powered by the radioactive decay of heavy elements. And those heavy elements were, there's still a debate, which I'll come back to, about what is the composition of this kilonova and what were the key radioactive elements that both powered the source and produced the either one or two components that that were seen, and also shaped the spectrum and the spectral series that we detected. The R process, which is produced when there is rapid neutron capture within an object like a kilonova, a neutron-rich environment, can produce three peaks labeled here: the first, second, and third peak, and this has been known for speculated about for several decades. The first peak around strontium and germanium, the second peak around xenon and barium, and then the third peak around gold and platinum. But the third peak also has either side of that, there's the lanthanides and actinides. And so exactly which of these peaks dominate or contributes to both the overall luminosity of the kilonova 17 GFO and its spectra are not that well constrained. And I'll come back to a discussion about that. And now, since then, since the discovery of 1708-17, we have been hoping for, even though we gathered a fantastic data set on that one object, it's still just one object. We'd like to see others and look for the diversity, perhaps, in this population. This is the second catalog of gravitational wave sources released by LIGO Virgo. And you can see here, this is mostly, it's dominated by black hole mergers, which have a pileup around 20 or 30 supermasses. And the neutron star mergers, we've got two definite neutron star mergers, the one 1708-17, of course, and then one from April 2019, for which no counterpart was detected, but of course that one was 150 megaparsecs, and also half the sky map was in daytime. ZTF covered the other half of the sky map, and we also did with Pan-STARRS and Atlas. ZTF covered more of it, in a more complete fashion, and no counterpart was detected. And there are a couple of neutron star black hole candidates as well, but again, no detection of a counterpart from those. So we've only got one detection of a neutron star merger in the local universe with a gravitational wave detection. But for the last decade, we've been surveying the sky for optical transients, and certainly true that 2017 GFO, the kilonova associated with the binary neutron star gravitational wave event, was reasonably bright, of order that similar to the faint end of the supernova luminosity function. If you go to the TNS page, the transient name server, this is our IAU transient name server for all astronomical transients that we think are extragalactic. Now, some of these that have been registered are galactic transients, but the goal of the transient name server is to have one place for all of our candidate extragalactic transient candidates. You can see that many of the surveys excise the galactic plane from their registrations on the TNS. And so we've been registering public astronomical transients and confirmed supernovae since January 1st, 2016. There's 64,000 transients registered on the TNS, and that's mostly Pan-STARRS ZTF, and then Gaia and Atlas are the next largest contributors to that 64,000 objects. Now, given that we have such large numbers of astronomical transients, and given that AT 2017 GFO was quite bright, very fast decline, but very similar to the luminosities, the peak luminosities, the peak magnitudes of type 1c supernovae and some of the fainter type 2 supernovae. And so this is a simple plot of a typical type 1c supernova, which is on the faint end of the luminosity distribution, but it's not unusual by any means. Similar for a type 2 supernova, this is one of the fainter ones, which again is relatively common by volume, but it's down around -15. And so you can see the kilonova actually peaked brighter than one of the more common faint type 2 supernova classes. So is it feasible that within the 64,000 astronomical transients, there could be some kilonovae lurking within our catalogs that we have not recognized? We're just looking at the numbers that we might expect. And so the number of binary neutron star mergers per gigaparsec per year is 320, within a factor of 2. That's the recent LIGO-Virgo collaboration estimate from the first half of 03. So 320 per gigaparsec cube per year. And the number of supernovae of all types is 125,000 per gigaparsec cube per year. So the ratio is about a factor of 400. 1 gigaparsec cubed would stretch out to a redshift of 0.15 approximately. And so we would expect around 300 binary neutron stars within that volume. They're not luminous enough to be detectable by most of our surveys within out to redshift 0.15. Just pick 1 gigaparsec here to illustrate them to the numbers. But let's say within 100 megaparsecs per year, within which a typical kilonova here at -15 would be 20th magnitude. So the number within 100 megaparsecs, and 20th magnitude is well within range of many of the surveys that I showed on the TNS plot. We'd only expect about 1 per year within 300 megaparsecs. And within 5 years, about 6 or 7 perhaps we might expect. So over the course of the last 5 years, we might have expected to have about 6 or 7 binary neutron star mergers and potentially kilonova. We don't yet know what the luminosity function of kilonova looks like, of course, but we might have expected to have to find 7 of these or so in the last 5 years. So we've been looking on GTF, of course, have been searching for these, and PTF before have been searching for fast transients. With Pan-STARRS and Atlas, we've been looking for these, particularly since 2017. But what we've done recently is go back and look at the full archive of all transients discovered by Pan-STARRS first, and then I'll talk a little bit about Atlas. We've gone back and looked at all transients within which are potentially associated with galaxies to a distance of 200 megaparsecs. And that association radius we use is about 50 kiloparsecs. And so we find nearly 1,900 transients within that distance. So it turns out that 873 of those have been classified by the community in general, including us, but mostly the community. So we rule those out as being kilonovae. 689 from their light curve. So we have some light curve data for those, either from Pan-STARRS or by going and looking at other surveys like Atlas and ZTF. And from those, we can rule out another 689. They have got supernova-like light curves and supernova-like luminosities, given their association with the host galaxy. So we rule those out as being very unlikely kilonova. Then we rule out another 128, which are 2 magnitudes brighter than we'd expect for a kilonova. And so that the plot in the top right shows you all of these transients which are classified or unclassified, and the dark line is 2017 GFO, the luminosity observed magnitude versus redshift. We've got 200 or so that we've done, 219 that we can't quantify any further because we've just got one data point and no other information. And it turns out with this, what we were looking for were objects which were of similar luminosity to 17 GFO, and with some indication that they decline quickly. That's a key characteristic of 17 GFO and kilonovae, given that they have to have low ejecta masses, and therefore it's very difficult to see in the optical how they could have a long duration light curve. So the two objects popped out. You can see here we just plotted peak luminosity versus the gradient of their light curve in magnitudes per day. So we're looking for objects that fade, that sit outside the two dotted red bars. All of the supernovae sit within those. There's only two objects, so 17 GFO is plotted as a blue point here, just to show you the reference point for the one known optical kilonova that we have. Two objects popped up. Pulsar's 15 CEY, which we don't think is a kilonova, which I'll come back to. And this object, PS17 CKE, which you can see here, quite faint, down around -11 or so, -11, -12, at a rapid decline, but only a limit on the decline. And so Owen McBrien, my PhD student, has a paper out on this, on these two objects, this summary of our search on the two objects that we found. And so this is a curious object. I have to say, if you ask me, do I think this is a kilonova, I'd probably say no. And I don't think it is, but we just present the data as we have them, and it's not impossible that it is. So this object was discovered in a very nearby galaxy, only 14 megaparsecs, NGC 4532. So you can see it here in this triplet of images with the green crosshairs. So that's the target image, the reference, and the subtraction. So it's clear here. We actually detected it on 8 separate images on the one night. We had overlapping images of that just region of sky by chance. Usually there's 4 images per night in Pan-STARRS. This was the 8 images taken. It was detected in all 8 images, so it's clearly a source. There's no movement over those 8 images. We then saw a rapid fade over a period of 4 nights. It disappeared in the Pan-STARRS data. So you can see that the next observation from Pan-STARRS was 4 nights later. It had disappeared by then. There's a possible detection in the NT. We tried to observe it with pesto 6 days later on the NTT, and also with SALT. Observations were attempted. The object was not detected in the acquisition image from either of those. We got a deep reference image for the NTT, and there is a marginal detection of an object 6 nights later when we do that careful image subtraction. So here's an object which was nearby, faint, and faded rapidly. At the time, we didn't do anything with it because if you look at the date here, 2017 April 16th, this was discovered before GW 170817, and at that stage, although people were aware of what kilonova might look like, no one was really, I think we're not motivated enough to chase faint transients that faded quickly, because we had so many other transients, bright transients, say with Pesto and with Pan-STARRS and Atlas, so many other transients which were bright and rising rapidly and looked particularly interesting. This one just fell off the shelf, really. We took some data of it. Nothing was observed, but it wasn't until after 1708-17 that we realized that a fade like this is significant in the context of So what does the light curve look like? And is it a possible kilonova? Of course, you will look at that in the distance of 14 megaparsecs, and alarm bells will be ringing that this is probably, given the nearby distance of this, that the probability of finding a kilonova at 14 megaparsecs is probably low, particularly given the rates that we now know. And I would accept that argument as probably the strongest argument against this particular kilonova. But the source itself, if you look at the light curve, and again, it's a very sparse light curve that we have. So we have the confident detection here at 0 days. That's the red point here at 0 days. A possible detection, or 5 sigma upper limit at 6 days in the NTT image. A definite non-detection at 4 days in Pan-STARRS. another non-detection 11 days later. No detection ever in the history of Atlas or Pan-STARRS at this position. There's a possible detection at minus 13 days. We have an image, we have several images from Pan-STARRS at minus 13 days. And it's a difficult image subtraction for these images, mainly because the images are through the W band filter. The image quality wasn't great, and the sky background, the galaxy background is very high at this position. And all of those factors produce suboptimal difference images. We've tried this with several people have tried to reproduce the difference images or recalculated the difference images. So we've done it, Armin Rest has done it, we've put it through the normal Pan-STARRS pipeline. And so there is excess flux apparently at minus 13 days. We're not convinced it is a clear detection of a point source. If it was, then I think it rules it out being a kilonova. It's hard to see a kilonova have this sort of light curve, but it's potentially an upper limit. So we're not sure about that point, whether or not that is a true detection of a point source at the position, even when we force it. All the other, the colored arrows are the Atlas upper limits. So there wasn't an obvious bright source that popped up and declined in this period. The gray triangles are 17 GFO, which indicates that the decline rate is similar to the one known kilonova that we have. Now, in 2017, in April, LIGO, of course, was working. Virgo was not. LIGO was up at the time, and the pink stripes represent the time when both detectors were off. So the probability of not detecting it, because of course, at 14 megaparsecs, if this was a binary neutron star merger, it would have been a whopping signal in both LIGO detectors. Neither of them detected anything around the time, reported anything around the time. Almost certainly there isn't any detection of anything of significance. Could have been that it was missed in these pink regions of downtime, depending on how you calculate the estimate of the merger time, which is very uncertain. It's about only about a 10% chance that that it was missed in terms of its merger time. But of course, that depends on how accurately you can estimate the merger time, which is the answer that is not very accurate. So I would say, given the evidence here, it's clearly we think it's a real fast declining transient. There was no GW source. The chances of missing it in the gravity in LIGO are probably 10% or less. I suspect it may be an LBV outburst that is never repeated before. It could be a foreground object. I don't think it's a mover. There's no hint of movement at all in the Pan-STARRS data. So I suspect if we go back with HST, which we'd like to do, I suspect we may see a stellar point source at that position, and it may be a luminous blue variable or some sort of luminous stellar outburst at that position. We've done the same in search in our Atlas data for all transients, this time within 100 megaparsecs. For Pan-STARRS, we looked at everything within 200 megaparsecs, but given that Atlas is a smaller facility, the telescopes are 0.5 meters rather than 1.8 meters as for Pan-STARRS. Then I think John Tonry has given you a talk here on Atlas before. So Atlas, at the minute, we have 2 telescopes in Hawaii, with 2 more coming online this year in Chile and South Africa. Each of them are 29 square degrees. So we get to about 19.5 sensitivity of 19.5 in dark time. We observe 4 times per night. And when the 2 telescopes come online in this year, it should be the whole sky, or certainly the whole sky between minus 50 and plus 50, and every night, 4 times a night, every night. And we've just released our forced photometry server. So if you want, you have access, the public can have access to Atlas data across the full history of the Atlas survey, and through a forced photometry server, and you can request measurements at any position in the sky over the whole survey timeline. So with Atlas, we've done exactly the same thing as for pan-STARRS. We've looked for sources which are matched with galaxies within about 50 kiloparsecs of galaxies within 100 megaparsecs to search for any unusually faint or fast declining transients. Again, we haven't found any within these. We found a few candidates, but we ruled them out as being foreground CVs in chance coincidence with host galaxies. But Atlas is quite a well characterized survey. Every image is well characterized. It's a well measured sensitivity limit. We can do force photometry at any position to check the sensitivity limits. Owen McBrien, my PhD student, has written a simple simulation survey, recovery efficiency calculator for Atlas. And so we can simulate 100,000 objects, for example, and calculate their rate of recovery. So we require 3 5 sigma detections. And this is our recovery map for objects like 17 GFO if we place them at 60 megaparsecs. I think there's about 100,000 objects here at 60 megaparsecs. It shows you the galactic plane, where the extinction in the galactic plane would reduces our sensitivity to those extragalactic transits. So we can estimate our recovery efficiency for those and do a Monte Carlo simulation. And so it turns out we haven't found any of the candidates which are like 17 GFO. And it turns out our upper limit on those is pretty much similar to the ZTF rate that Igor published last year, less than about 1,800 per gigaparsec cube per year. That's the upper limit on the number of kilonovae of similar luminosity to 17 GFO. And we find about 1,500 or so. So within the uncertainties, it's pretty similar. The new LIGO rate, of course, is only 320 per gigaparsec cube per year, so significantly lower than both of our optical estimates. There are some of the other estimates from binary neutron stars and galactic pulsars, double neutron star systems here. And so they're all, obviously the LIGO rate is currently the best one, and that may well come down with the data that they can add from the second half of 03. Okay, but so one thing we did find, so we haven't found any, no one has found any convincing kilonova candidates, and I think PS17CKE for me is not a convincing candidate for the reasons I mentioned. But we did find this one extremely fast declining object, much more luminous than 17 GFO. It's called AT2018KZR. So this was actually jointly discovered. It was first discovered, ZTF discovered it first, and we detected it several hours later with Atlas. And I noticed this, and we noticed this here, when we saw the Atlas light curve come in a few days later. It rose rapidly and then declined quickly. We took an image with it was particularly blue in the ZTF G and R filters in comparison to the Atlas orange filter, which is an R and I composite. It's pretty luminous, 2.5 magnitudes brighter than the kilonova, but we watched it fade rapidly. And then we triggered many telescopes to observe it. We were fortunate to get on it, to recognize it quickly and get on it quickly. And it was really the combination of both surveys that alerted us to its unusual nature. So what actually is probably the fastest declining object after 17 GFO in terms of optical surveys. And at the time we thought, well, this could be a candidate, a kilonova candidate, very luminous. And much more luminous, so it does need an extra powering source to produce the luminosity, and it pushes it up to around 10 log L here of 43, 10 to the 43 ergs per second. So the peak magnitude and the fast decline rate implies that we need some sort of powering source, which is so a power law, which has got an exponent of around -2, even -5.3, If you put that into a simple light curve code, then that works reasonably well to reproduce the decline in luminosity that we see. So the red points here are 2018 KZR. The black line is one which is powered by this simple powering model, which has got this analytic function for the powering, and the exponent is around -2. So that is what you would expect for an object which is powered by a magnetar or a magnetic neutron star, which is spinning down due to magnetic dipole radiation. So that model, that magnetar model, has been around since Kaysen and Bilstein and Stan Woosley came up with it to account for the superluminous supernova that were discovered in these surveys, but these wide field surveys, but it can be applied to other fast transients. Now, it's quite a flexible model, but it's just illustrating that with a power source, with a central powering source such as that can reproduce the luminosity. It's not possible to produce the luminosity and the decline rate with nickel only. The ejecta mass needs to be about 0.1 solar masses to get the narrowness of the light curve for an opacity of somewhere between 0.1 and 0.2. But the peak requires 0.2 solar masses of nickel 56. So there's not a physical solution that can produce this light curve, the peak and the decline rate with radioactive nickel 56. You can see some of the broader light curves here are objects or models which are an object 2015 K, which is explainable by nickel 56, a low amount of nickel 56 and a low ejecta mass. But the models and the objects that we think are driven by nickel 56 are significantly broader than the light curve observed for this object. So what do we think it is? A clue to this of its nature is in the spectral analysis. So we run a spectral analysis code here called TARDIS, which is written by Stuart Sim and Wolfgang Kersendorf. Stuart Sim works here in Belfast, as many of you know. So this is again, it's a Monte Carlo code similar to the methods that were produced by Neil and Lucy in the 90s. Dan Kaysen's model is a Monte Carlo code. Sedona is a Monte Carlo code, but it's a bit more, is significantly more sophisticated than TARDIS. TARDIS produces. In TARDIS you can give it a single zone model. You can give it a layered structure, and it will follow the packets as the ejecta expands homologously. It is one-dimensional. It is LTE, and it assumes a black body at the base of the photosphere. So it's not. There are more sophisticated codes for modeling supernovae and transients that exist, such as Sedona, CMFGen, ARTIS, and Python, which many of them are non-LTE and three-dimensional. And so those are more realistic codes, but the advantage of TARDIS is that we recognize its limitations, but it is fast, and we do have the ability to run many hundreds of models and then explore composition profiles, density and velocity profiles, which allows us to get reasonable estimates of the composition. And it's been used quite extensively for type 1a supernovae. It is dependent, as all of these codes are, on. Sorry?
5 minutes, please.
Thanks. So this depends on reliable atomic data. Oops. So I just hit the wrong button. Okay, let me put that back up. So we've used this, and my student James Gillanders, who I highlighted at the start, has used this code to model 2018 KZR. So the black line here is are the observational data, and the red lines are the TARDIS models. We've got 3 early spectra taken in the first 4 days. These are epochs after peak, and so probably the earliest we have is somewhere between 3 and 6 days after exploding. So you can see we can reproduce the strongest features. Now, the strongest features in this spectra are due to mostly iron lines, blends of iron 2 and iron 3 that you can see labeled here. Overall, the composition is very well reproduced by oxygen, magnesium, and silicon. The bulk of it is oxygen, magnesium, and silicon, which we suggest is compatible with an oxygen neon magnesium white dwarf. There is very little carbon, and that is reasonably well constrained from several carbon lines you expect to see in this region of the spectra. The important thing here is that we've got a very large mass fraction of iron in comparison to nickel and cobalt. So given that these are very early, it's hard to see how that iron can have come from radioactive nickel and cobalt. So that's the main result from this. It's quite a blue spectrum, so it's hot. And these lines are well known. We see these lines in type 1c spectra, but we usually see them after peak when the spectra have cooled significantly. These are detected very strongly when the photosphere is hot. And the only way we can produce these is a large mass fraction, a large abundance of iron of some. So if we think what isotope of iron that might be, it's difficult to see how it can be iron 56 because that can only be produced through the decay of nickel and cobalt. And given that the half-life of cobalt is 77 days, there just isn't a way to get this iron to cobalt ratio through normal nucleosynthesis of the intermediate mass elements to nickel, which then decays to cobalt and iron. So we propose that it's another form of iron, that it could be iron 54. And again, the reason for that is just these lines which are due to the iron blends are extremely strong for the temperature that the spectrum is at. So we suggest that it could be iron 54, that it can't be iron 56. The significance of that is that Brian Metzger, Ben Margulit have produced estimate composition of the ejecta from the tidal disruption of a neutron star and white dwarf, or a neutron star and a black hole. And the compositions match reasonably well if this is an oxygen neon white dwarf, which is disrupted by the stellar mass black hole. Now, the compositions match well. You can see iron 54 is here in the left plot. That's a carbon oxygen white dwarf, of course. And iron 54 is prominent in the right-hand plot from Brian Metzger's simulations, and it's dominated by oxygen, magnesium, and silicon. So we think the composition and the velocity distribution match reasonably well these projected models of neutron star white dwarf mergers or neutron star black hole mergers. So what the thing missing, of course, here is the powering mechanism. So it might be that if it was a neutron star, it could be a magnetar could be produced, and Metzger papers speculate on that. There's also speculation in these papers that disk wind shocks can produce a power source which is similar to that from a magnetar. So this might be the best explanation. Let me finish off. So we think it's a fast declining transient. The light curve is not explainable by nickel 56. We need another powering source, and the composition would suggest an unusual composition with a very high iron abundance, which we don't think can be iron 56, and it's more likely to be iron 54 produced in an environment like this. Given the power of the spectral composition analysis and how that impacts the understanding of these transients, we've gone back to the spectra of the kilonova 17 GFO, and I think that the quality of the spectra that we have overall the projects and facilities that observe this has probably not been appreciated by everyone. We've got a spectra every day from 1.5 days to 10.5 days from the UV cutoff right out to 2 microns, and the spectra quality are quite high. We can calibrate those exactly to the photometry, so we know these are well calibrated spectra. These are all the X-shooter spectra here, but there are others. If you want to access to these fully calibrated X-shooter spectra, you can go to the Engrave webpage and get them. But there are other telescopes that have got high quality data of across this region as well. And up until now, there hasn't been, I think, maybe a surprising lack of detailed analysis of all of these spectra together to work out what elements can we see in the spectra, given the number of different codes that are available. And I know several groups are working on this in parallel. This sort of summarizes, I think, most of the work which has been done on spectra. So we suggest that some of these lines in the early spectra could be tellurium and cesium. Reasons why that might not be correct, which we would accept. Darrell Watson suggests that the line here in the early spectra of 17 GFO could be due to strontium, and that's from the first peak of the R process elements. Of course, Dan Casey's models overall work pretty well to describe the overall spectral energy distribution, but haven't reproduced the features in detail, if these are features that can be identified with individual sources. So just let me remind you that at the time of GW17 or 817, we all thought we discovered gold and perhaps platinum. Here are three of the press releases, and I accept that I shamefully took part in this process of claiming that the heavy elements had been discovered and these merging neutron stars scatter gold and platinum into space. But what really is the evidence for either gold and platinum being produced in this? Given the rate of binary neutron stars of 320 per gigaparsecs per year and the solar abundances, we all think that any individual neutron star could produce around 10 to the minus 3 of platinum and gold. And so that's similar to some of the nucleosynthetic calculations that have been done as well. So an ejecta mass of 10 to the minus 3 of platinum or gold is plausible for these. So could we detect that? Well, recently our atomic physics group at Queen's here have produced new calculations for platinum and gold. Counterbalance, and particularly Michael McCann, PhD student. So they do this all the time for heavy elements. They haven't done gold and platinum before, but they've just recently calculated these, and they've given the data to us. So this paper should appear on arXiv on Friday. They've given the data, new atomic data to us to put into TARDIS and do some simple calculations. So James, Gil Anders, and Michael have worked on this together. Here's an example of the regions of gold where these are potentially forbidden lines that they've predicted. So we put this into TARDIS and asked the question, so if you had 10 to the minus 3 solar masses of platinum and gold, would you actually see it in the spectra? So we think early on there are lines which are prominent, but they're in the UV and they're almost certainly going to be blended with other lines in the UV. So we think in the early spectra of kilonova, it's going to be very difficult to distinguish the isolate elements of platinum, to isolate the two elements, platinum and gold, from other elements that might produce absorption lines in the near UV. So you can see some of the absorption lines here, which are the lines under the gray curve. Those are the strongest lines that produce these features in a kilonova with this ejecta mass and a velocity of about 0.2 c on a sensible density profile.
Sorry, Stephen.
One interesting thing we point out in this is that, and this is where I'm nearly finished, the atomic data do predict a number of low-lying electric quadrupole or magnetic dipole transitions, which are likely to be forbidden lines. And almost certainly the ejecta, at least some of the ejecta from 17 GFO expanding at 0.2 c, only a few tenths of or less than a tenth of a solar mass, a few hundredths of a solar mass, it probably has gone nebular within 2 to 3 days. So we predict that there would be forbidden lines of the heavy elements that could appear within a few days. And if you look at the late spectra of 17 GFO, there are a number of broad features that appear. They've all got half widths of about 0.1 c. It could be that's coincidence and they're not really individual lines, or they're more complicated blends. But each of these broad features, right from 7 days, 5 days to 10 days, have a very similar half width. So it's possible that these could be dominated by forbidden emission lines in the spectrum of 17 GFO. These show you the positions of the lines for platinum and gold. So there isn't a clear coincidence of these. There's a hint that platinum could explain the 1 micron feature, or a little bit of the 1500 micron feature, and some of the wing of the 7500 feature. But that's as far as we could tell. I think the positive thing, though, is that our predictions from simple predictions of what the strength of these lines, they should be about 10 to the 38 ergs per second, which is of order the strength of the observed features in the spectra in 17 GFO. So we think this is interesting enough to pursue in the future, both with new objects and with calculations of other heavy element atomic data to repeat the process. So I think in summary, we don't find significant evidence of platinum and gold, either in the early spectra or in the late spectra, but particularly in the late spectra, the strength of the forbidden lines we might expect is about the same as we can measure in that spectrum. So I'll finish with my summary. Wide field optical surveys have changed the landscape and discovery space in this field. We need physical powering processes beyond radioactive nickel-56, magnetars, or black hole accretion or mergers may drive that luminosity. Stellar mergers do look like they are luminous and may play a very important role in chemical enrichment. Neutron star black hole white dwarf black hole mergers might produce significant amounts of iron 54. Spectral models are vital to determine the composition. That's an area that we're working on intensively here. But new atomic data are required for the heavy elements. We've no clear detection of gold or platinum in the spectrum of 17 GFO, but the line luminosities in this range are in the range of those measured. So this is promising for the future. Thank you.
Thank you very much, Stephen. Please raise your virtual Zoom hand if you have questions. Jim, please go ahead.
Hi, Stephen. This is Jim Fuller. Really interesting stuff. I had a question about 2018 KZR. Is there any strong argument against that being powered by some sort of circumstellar interaction or shock cooling of an envelope, which we see in some other rapidly fading transients?
So I think the only evidence there would be against it would be again the spectral, where we don't see any evidence of any narrower lines. We've got spectra to 14 days. We do see calcium, the permitted calcium line. The forbidden calcium, and also the calcium triplet. They look quite broad at that stage, and we don't see any evidence of narrower features and slower moving features that might be associated with some sort of larger, slower moving envelope. It would still need to be optically thick up until that point, and then go nebular but retain the line widths and without showing any evidence of narrower components. There's no multi-wavelength detection of it, so there was no radio or X-ray observation, so I can't say anything from that perspective.
Okay, but if your CSM is pretty compact, and then you're basically just seeing shock cooling of that envelope, that could potentially explain the light curve.
Yes, that would explain the light curve. Or you could explain the light curve in that way. Things still probably difficult to explain the iron abundance from that, unless there's a lot of iron within that primordial iron from the progenitor within that envelope.
Yep. Okay. Thanks.
Any other questions? Wenpin, please go ahead.
So I have a question on this PS17CKE. Is there any multi-wavelength follow-up for that one? I think presumably the radio follow-up can easily rule out a jet.
Yeah, so the radio follow-up is difficult. So Rob Fender and his team at Oxford did have did take some observation. I gave it this. I highlighted this a while ago when I was giving a seminar in Oxford, and so they decided to observe it. But if you look at the host galaxy, the background is extremely complicated. And in the radio as well, there's either diffuse radio emission around that area, because it's on a bright area of the host galaxy. So they needed to take, or they did take some observations, and I think they detected a source there, but it was almost certainly dominated by the host galaxy. They needed to take another image or a higher resolution image with a VLA. I don't think the VLA happened, but I'm not sure. But it was just difficult to disentangle any source, even with multiple epochs, to distinguish any time variable source given the galaxy background. There was nothing at the time, but they did try. It was about, I don't know, 300, 400 days later that they tried it.
Oh, thanks.
It's just a difficult object.
Yeah.
Also on the same, so Stephen, on PS17 CKE, on your summary slide, I wanted to highlight a point, the red point at minus 10.7 and 4 days. This was actually a classical nova that we had discovered with the Palomar 60-inch in the P60 fasting survey, which was incredibly red and very luminous. So if you go to your summary slide, you actually, have that point on that luminosity timescale plot. And this was discovered back, this red point that you see there, which is at minus 10.7. Yeah, right there. So that's actually a classical nova in M82 with very similar luminosity and redness as PS17 CKE, which we had discovered back in 2008. So this is 2008, November 29th. So I'm happy to send you more details about that. But sometimes classical novae can be very pesky in these searches too.
Yeah, we thought it was just a little bit too bright to be a classical nova, just on it's on the extreme luminosity end. But
absolutely,
then, as I say, I don't think it's. I'd be hard pressed to convince you it's a kilonova. So I think that's more like the explanation.
Right. Any other questions for Stephen? Okay, if not, let's thank him again for an exciting talk. And I'd request the faculty members to please stay on for the faculty meet and greet, and everybody else is welcome to sign off. Thank you. And Stephen will stay on the same Zoom line here. So just give people a second to sign off, and you're welcome.